Today we're going to be looking at extrema on an interval. So this is the first lesson in chapter 3, which is basically now using our derivative for different applications. And the first is going to be looking at extrema. Now, you are more likely used to hearing the word maximums and minimums, but basically these are called the extreme values, which is why we use the term extrema for the function. We are going to look at what's called optimization, so that is optimizing or finding the optimal point, either the highest or the lowest point for a specific function. So we actually have two different types of extrema. The first is an absolute or a global, which is what you are used to finding in your other classes. So basically, we are looking at either the highest or the lowest value over an entire function. Which is basically what that definition there is saying, is that it is the global max or min if and only if all of the other y values are either bigger or smaller than that y value. So, on this example, it says the graph of y equals h of x is shown below. To determine the extrema of h of x on the interval from a to f. So, we first want to find our global or absolute. I tend to use the word absolute more often than not, but you can use, and you will see, either one. So, note that at x equals, if I am looking at the lowest value of any of my values, x equals d, will be the absolute minimum, while at x equals e will be the absolute maximum. Now, continuing down your page, okay, we also have this idea of what is called a relative or local extrema, which you should have seen in pre-calculus. And basically, it's this idea that I can kind of cut off or look at just a portion of my graph, and for that portion, it is the lowest or the highest values. We can also think about these as turning points. So when my graph has to turn directions, I should have a relative minimum or maximum. So looking at our graph, we have a few more. So notice that we will also have a relative max at x equals c and a relative min at x equals b. Now, these are not the highest or lowest overall, but look, if I were to just cut off a chunk of my graph, that is the lowest point, or for C, it is the highest point of the stuff around it. So, when we're looking, our relative are going to be y values where the function changes from increasing to decreasing, or vice versa, which is why I call them turning points. And then our absolute is going to be the highest or the lowest y value of the entire function, or at least over a specific domain. Now, if there is an open interval, okay, containing C on which f of c is a maximum, then f of c is called a relative max. Same thing if there is an open interval containing c where f of c is a minimum, then f of c is called a relative minimum. When we say open interval containing c, we just mean that we can find some interval. That doesn't include the endpoints. The biggest thing to take away from that is that it is not including the endpoints. Okay, so our relative extrema cannot be endpoints. However, our absolute could still be at our endpoints. So going down, it says, in many cases we will be asked to analyze both open and closed interval functions. So this first one, notice that we have arrows, so that would be an open interval function. So it says, consider the graph of y equals g of x shown at the right, state the relative extrema. So notice, again, we're looking for turning points, or where we change from decreasing to increasing, or increasing to decreasing. So we have 3. We have relative extrema at x equals -3, 2, and 4. Next it asks us for what the absolute extrema are. So note that x equals -3 will be the absolute minimum. But on the opposite side, because these arrows go forever up, there is no absolute maximum. Now that changes a little bit on our next one. So notice that we do have endpoints on this. Okay, we stop at 0, 1 and 12, 6. So again, looking for the relative extrema. Remember that our relative extrema cannot be at endpoints. So we are looking at x equals 2, 7, and 10. Now, for our absolute, those can potentially be at endpoints, but they don't have to be. In this case, my lowest overall point is at x equals 2, is the absolute min, and my biggest tallest point overall is at x equals 7, is the absolute min. This goes on for us to see. So notice that in my first example, I did not necessarily have an absolute maximum because it went on forever. Likewise, if a function were to go down forever, it does not necessarily have an absolute minimum. However, if we have endpoints, because it stops and starts, and it's a continuous function, we will always have to have an absolute extrema, which leads us to the idea of our extreme value theorem. So basically it tells us that if f is continuous on the closed interval, then it must have both a maximum and a minimum value. By saying maximum and minimum, that means the absolute max and min. If it does not give a qualifier, like relative, then it means the overall. Extreme values can occur at interior points, which just means the stuff on the inside, or at endpoints. A function may both have a maximum and a minimum over the interval, either a max or minimum, or no extreme. It just depends on if it is continuous or not. So it says for each graph below, explicitly state where the hypothesis of EBT fails on the interval, then determine if the function has extrema. So if it's not continuous, then we cannot guarantee it, okay? But if it is continuous, we can guarantee it. So note on this one, EBT does not apply. However, it does have an absolute min at x equals 0 and an absolute max at x equals 1. Here again, we are not continuous, so EBT does not apply. This time, notice that we have an absolute max at x equals 0, but notice that we would want to have the absolute min at this point right here, but because it gets closer and closer and closer and closer, and there's a hole there, there will be no absolute minimum. So, looking at our next two, okay, again, EBT does not apply because we have all vertical asymptote there. And notice here we have neither, so we have no extrema because that top value is the one we would want to be our absolute max, but if there is a hole there, and then that arrow goes down forever at that asymptote, so there's no absolute min either, okay? On this last one, EBT also fails, okay, because these endpoints at the end, okay, we only have the open interval from 0 to 3 instead of the closed interval. Now we do have an absolute max at x equals 1 and an absolute min at x equals 2. So we are only guaranteed an absolute min and max if we are on continuous and if we are on a closed interval. However, that just tells us when it's going to happen, when we're continuous and when we're on a closed interval. However, that doesn't tell us how we can find it algebraically, which is what we're going to look at here in a moment. So looking at some functions now, instead of their graphs, we need to be able to again decide when we're going to be able to apply EBT. So on our first one, we're looking from -4 to 4. So notice that here EBT fails because f of x is discontinuous at x equals 2, which is in -4 to 4. Now, our next one is an E. Okay, so remember that our E graph is an exponential graph, so it's going to look like that, okay? So it is continuous. Even though we have a horizontal asymptote, it's still going to be continuous everywhere. So here, g of x is continuous. So EBT applies on -5 to 5. Okay. Lastly, notice that we have a square root. When we have a square root, we have to think about our domain. Here, we would have to be greater than or equal to -2. But notice that we are wanting to include all the way to -6, which we can't do. So h of x is continuous only for x is greater than or equal to -2. So EBT fails. 4, -6, 2, 6. So basically the idea is, remember that we talked about how our relative mins and maxes are like turning points, okay? We're changing from increasing to decreasing or decreasing to increasing. If we're looking at our graph of that, notice that we would have to have either a point up top or a point down low. And we have looked a little bit at how at those points, our tangent line, the slope of that tangent line is 0. And so if our relative extrema have to happen at those turning points, that also means that our relative extrema can only occur at a critical value, which basically that's what we're going to call when f prime of c equals 0. Now there is one other case, and that would be if I have something like our absolute value. So notice here, this is still a relative extrema, but our f prime does not exist instead. So we have to consider two different things. One, f prime is 0. 2, f prime does not exist, okay? And our relative extrema can only occur at a critical value, and our absolute extrema have to occur at a critical number or at an endpoint if we are on a closed interval. So this is what we can do to find absolute mins and maxes, is what we call the candidates test. And a candidates test basically allows us to find our critical values first, because those are going to be the candidates for our absolute mins and maxes. We then need to test and see which one of those is actually the biggest or the smallest. But do remember that we also have to include our endpoints for these problems. So let's look at some examples. Since find the absolute extrema of the function on the given interval, provided that EBT is applicable. If not, justify why. So notice that our first one is a polynomial function. Remember, we don't have to state anything more than polynomial function, continuous, we're good to go. We're looking at the closed interval, -1 to 2. So the first thing that we need to find are our critical points. And again, remember, that's where our derivative equals 0 or our derivative is undefined. So it's going to be helpful for us to have the derivative. So f prime of x here is going to equal 24 x squared minus 6x minus 9. And we want to know where that thing equals 0. Notice that since it's a polynomial function, we don't have to worry about it being undefined anywhere, which is nice. So we would then factor it, and we're going to get 4x minus 3 and 2x plus 1. So our x's are going to equal 3/4 and -1/2. But remember that our absolute extrema can happen not only at critical points, but also at endpoints. So we also need to think that we have endpoints at -1 and 2. So from there, we're just going to make a table of values. This is going back to my original function. So I'm going to go ahead and label it as f of x so that we don't get confused about what I'm plugging into. And then we're just creating a table of values. So I have -1, -1/2, 3/4, and 2. This does show that it is calculator active, so then we're just plugging and chugging into our calculator. So for -1, we have 0. For -1/2, we have 4.75. 3/4, we have negative 3.063, and at 2, we have 36. So notice that our absolute max is at 2, 36, and our absolute min is at 3/4, negative 3.06. Now it is important, sometimes they're going to ask you the location of your absolute mins and maxes, and that's going to be an x value. If they say what is the what is the absolute minimum value or the absolute minimum or maximum value, it's actually asking for the y value. Here it's just asking for the extrema, so I'm going to list them as a point. Continuing on with our next one, it's very similar. Again, I have an x, which is just a polynomial, and then we have a trig function. It's a sine, and sine is continuous everywhere, so EVT will apply. So again, I start by taking my derivative. I get 1 minus 2 cosine of x. I'm setting that equal to 0. So I want to know where cosine of x equals a positive 1/2. That's going to happen in our first quadrant at pi over 3, and in our fourth quadrant at 5 pi over 3. Notice that my interval is from 0 to 2 pi, so I don't have to worry about it being anywhere else. Now on my function this time is g of x, so I'm going to go ahead and label. We have 0, pi over 3, 5 pi over 3, and 2 pi. Again, I have to include both my critical points and my endpoints. Again, it is calculator active, so just plugging in to our calculator to fill out our table. We have an absolute max at 5 pi over 3, 6.968, and an absolute min at pi over 3, negative 0.685. Now, one question that I tend to get is what happens if I got the same value. So notice like 5 pi over 3 and 2 pi are pretty close. If you got the same value, then you would just lift both of those. So like you would say, if say 5 pi over 3 and 2 pi were both 6.968, I would just say absolute max at 5 pi over 3, 6.968, and 2 pi, 6.968. In this case, they're different, so you just get 1. Lastly, on this one, we have h of x. So again, I'm taking my derivative. Now we do need to be careful because here we have a sine squared. So remember that that squared is outside of the whole thing. So we need to use our chain rule. So I bring down my 2. 2 sine of x is now to the first power. And then I also have to multiply by the derivative of the inside stuff, which gives me cosine. Then my derivative of cosine is a negative sign, but I already have a negative there, so I have positive. We're setting that equal to 0. Notice that I have a sign on both of those, so I can factor that out. So this time we're looking where sine equals 0, which is going to be at 0 and pi, and then where cosine of x is negative 1/2, which is going to be in our second and our third quadrant. So again, making my chart, I have a h of x this time. Again, you can put y, but it's just important, like for a free response question, sometimes we have multiple functions, or we have a function and a derivative. So it can be helpful to go ahead and label that table with the function that you're talking about. So here we have 0, 2 pi over 3 pi. I'm going to go ahead and do a second set for our 4 pi over 3. And notice here we are stopping at 3 pi over 2. Again, plugging into my calculator, I get -1, 1.25, 1, 1.25, and 1. So we have a absolute minimum value of -1 and an absolute maximum value. And we can just say, if we're talking about the value, I can just say it's at 1.25 because that's the same value at both 2 pi over 3 and 4 pi over 3. If it asks you to like list the points, then you would just list both of your points. Couple more here. So notice on D, we have to be careful because D is a natural log. Likewise, we have to be careful on our last one because we have a root. So thinking about our natural log, okay, remember that just our normal natural log of x function has a vertical asymptote because the inside is not allowed to equal 0. On this function, because we have x squared minus 9 on the inside, if we look at where that would equal 0, we get a plus or minus 3, and positive 3 is within that interval that they give us. So we would say f of x is not continuous on -2 to 5. Therefore, so remember our 3 dots means therefore dbt does not apply. Now, with our next one, we do have to consider what this root is. Okay, if it was a square root, remember our inside has to be positive. This one is a cubed root. And so we are allowed to get negatives with a cubed root, which means that we would be able to use our EDT because it will be a continuous function. So on this one, again, you're going to apply your derivative, so your derivative equal to 0, and then you're going to make a chart. On this one, you would have to think about where it is going to be undefined instead, because you are going to end up with a fraction on your derivative instead of a nice pretty polynomial. So if I take the derivative of this, so this is technically x minus 2 to the 2/3. We would have to do a chain rule. So we get 2/3 times x minus 2, and if I subtract 1, we would get a negative 1/3, or a 1/3 on the bottom. Then if I multiply by the derivative of the inside stuff, well, the derivative of x minus 2 is just 1, so I don't really have to worry about anything. So this is what I was talking about, is where if we set this equal to 0, so notice that this is the cubed root of x minus 2. Notice that there is no way that that can equal 0, because basically we would be looking at where the top equals 0, and that doesn't happen. However, notice that this is h prime of x does not exist at when our denominator equals denominator equal to 0, divide by 3, cube both sides. I still have x minus 2 equals 0, so it's not going to exist at x equals 2. And remember that those have to be included in our candidates test, just like they do when it equals 0. So I'm looking at 1, 2, and 10. If I plug that in, we get 1, 0, and 4. So I have an absolute min at 2, 0, and an absolute max at 10, 4. So biggest things to remember is that if I'm looking for an absolute minimum or maximum, we include both our critical points and our end behavior, or sorry, our end points. Next section, we will be looking more at how to tell if things are relative minimums or maximums.